Hello dear students, today is the third recorded lecture for our course Mathematical Statistics. We will take the following definition. Let x and y be a random variables with joint probability distribution f x and y. The covariance of x and y is sigma x and y equal expected value of x minus mu x times y minus mu y equal summation of x summation of y for x minus mu x times y minus mu y times f of x and y if x and y are discrete, and sigma for x and y equal expected value of x minus mu x times y minus mu y equal integration for x from minus infinity to plus infinity, integration for y from minus infinity to plus infinity, x minus mu x times y minus mu y times f of x and y dx dy if x and y are continuous. The covariance between two random variables is a measure of the nature of the association between the two. If large values of x often result in large values of y, or small values of x result in small values of y, positive x minus mu x will often result in positive y minus mu y, and negative x minus mu x will often result in negative y minus mu y. Thus, the product x minus mu x times y minus mu y will tend to be positive. On the other hand, if large x values often result in small y values, the product x minus mu x times y minus mu y will tend to be negative. The sign of the covariance indicates whether the relationship between two dependent random variables is positive or negative. When x and y are statistically independent, it can be shown that the covariance is zero. The converse, however, is not generally true. Two variables may have zero covariance and still not be statistically independent. Note that the covariance only describes the linear relationship between two random variables. Therefore, if a covariance between x and y is zero, x and y may have a nonlinear relationship, which means that they are not necessarily independent. The alternative and preferred formula for sigma x and y is stated by the following theorem. The covariance of two random variables x and y with means mu x and mu y respectively is given by sigma x and y equal expected value for x and y minus mu x times mu y. The proof: for the discrete case, we can write sigma x and y equal summation for x, summation for y, x minus mu x times y minus mu y for f of x and y equal the following. Since mu x equals summation x for x times f of x and y, mu y equal summation y for y times f of x and y, and summation x summation y for f of x and y equal 1. For any joint discrete distribution, it follows that sigma x and y equal expected value for x and y minus mu x times mu y minus mu y times mu x plus mu x times mu y equal expected value of x and y minus mu x mu y. For the continuous case, the proof is identical with summations replaced by integrations. For example, from the previous example, it describes a situation involving the number of the blue refills x and the number of red refills y. Two refills for a ballpoint pen are selected at random from a certain box, and the following is the joint probability distribution as shown in the following table. Find the covariance of x and y. From the example, we see that expected value of x and y equals 3 over 14, and the mu of x equals 3 over 4, and the mu of y equal 1 over 2. Therefore, sigma x and y equal expected value of x and y minus mu x times mu y, which is equal 9 over 56. Another example, the fraction of x of male runners and the fraction of y of male runners who compete in marathon races are described by the joint density function as following. Find the covariance of x and y. We first compute the marginal density functions. They are g of x equal 4 x with power 3, and x is between 0 and 1, and h y equal 4y times 1 minus y square, which y is between 0 and 1. From these marginal density functions, we compute mu of x, which is equal to 8 over 15. From the joint density function given above, we have the expected value for x and y, which is equal to 4 over 9, and the sigma of x and y equals the expected value of x and y minus mu x times mu y, which is equal to 4 over 9 minus 4 over 5 times 8 over 15, which is equal to 4 over 225. Although the covariance between two random variables does provide information regarding the nature of the relationship, the magnitude of sigma x and y doesn't indicate anything regarding the strength of the relationship, since sigma x and y is not scale free. Its magnitude will depend on the units used to measure both x and y. There is a scale-free version of the covariance called correlation coefficient that is used widely in statistics. Let x and y, this is a new definition, let x and y be random variables with covariance sigma x and y and standard deviation sigma x and sigma y respectively. The correlation coefficient of x and y is rho x and y equal sigma x and y over sigma x times sigma y. It should be clear to the reader that rho x and y is free of the units of x and y. The correlation coefficient satisfies the inequality of rho x and y is between or equal minus 2 and 2. It assumes a value of 0 when sigma x and y equal 0, where there is an exact linear dependency. Say that y equal a plus bx. Rho x and y will be equal 1 if b greater than 0, and rho x and y equal minus 1 if b is less than 0. The correlation coefficient is the subject of more discussed in the following chapter, where we deal with linear regression. Find the correlation coefficient between x and y in the previous example. So the expected value of x squared will be equal 27 over 28, and expected value for y squared will be equal 4 over 7, and sigma square for x will be 45 over 112, and sigma square for y will be equal 9 over 82. Therefore, the correlation coefficient between x and y will be minus 1 over root of 5. Find another example. Find the correlation coefficient of x and y in example 4.14. The expected value for x square will be equal to 2 over 3, and the expected value for y square will be equal to 1 over 3. We conclude that sigma square x equal 2 over 75 and sigma square y will be equal 11 over 225, and the row x and y equal 4 over the root of 66. Note that although the covariance in example 4.15 is larger in magnitude than that in example 4.16, the relationship of magnitudes of the correlation coefficients in these two examples is just the reverse. This is evidence that we can't look at the magnitude of the covariance to decide on how strong the relationship is. Another new topic is means and variance of linear combinations of random variables. We now develop some useful properties that will simplify the calculations of means and variances of random variables that appear in the later chapters. These properties will permit us to deal with expectations in terms of other parameters that are either known or easily computed. All the results that we present here are valid for both discrete and continuous random variables. Proofs are given only for the continuous cases. We begin with a theorem and two corollaries that should be reasonable to the reader. The first theorem: if a and b are constants, then expected value for a times x plus b will be equal to a times expected value of x plus b. An example: applying the theorem to the discrete random variable f of x equal to x minus 1. Rework on the example 4.4. According to the theorem 4.5, we can write expected value for 2x minus 1 will be 2 times expected value of x minus 1. Therefore, the expected value of x will be 41 over 6. Therefore, mu 2x minus 1 will be 2 times 41 over 6 minus 1, which be 12.67 as before. Applying theorem 4.5 to the continuous random variable g of x equal 4x plus 3. So the expected value for 4x plus 3 will be equal 4 times expected value of x plus 3, which is equal to 8. Another theorem: the expected value of the sum or difference of two or more functions of a random variable x is the sum or difference of the expected values of the functions. That is, expected value of g of x plus or minus h of x equal expected value of g of x plus or minus expected value for h of x. An example: let x be a random variable with probability distribution as follows, as in the following table. Find the expected value of y, which is equal to x minus 1 square. The expected value for x minus 1 squared will be equal to the expected value for x squared minus 2x plus 1, which is equal to expected value of x squared minus 2 expected value of x plus expected value of 1, and the expected value of 1 equal 1, which is equal to, finally, is equal to 1. Another example, the weekly demand for a certain drink in thousands of liters at a chain of convenience stores is a continuous random variable, which is g of x equal x squared plus x minus 2, where x has the following density function. Find the expected value of the weekly demand for the drink. The expected value for x squared plus x minus 2 will be equal to the expected value for x squared plus the expected value for x and the expected value for 2, and we said before that the expected value of 2 will be equal to 2, and the expected value for x squared plus x minus 2 will be equal to 5 over 2. So the average weekly demand for the drink from this chain of efficiency stores is 2,500 liters. Suppose that we have two random variables x and y with joint probability distribution f of x and y. Two additional properties that will be very useful in succeeding chapters involve the expected value of the sum, difference, and product of these two random variables. First, however, let us prove a theorem on the expected value of the sum or difference of functions of the given variables. Theorem 4.7, the expected value of the sum or difference of two or more functions of the random variables x and y is the sum or difference of the expected values of the functions, that is, expected value of g of x and y plus or minus hx of and y equal expected value for g of x and y plus or minus expected value for hx and y. If x represents the daily production of some item from machine A and y the daily production of the same kind of item from machine B, then x plus y represents the total number of items produced daily by both machines. Corollary 4.4 states that the average daily production for both machines is equal to the sum of the average daily production of each machine. Let x and y be two independent random variables, then expected value for x and y equals the expected value of x times the expected value of y. Theorem 4.8 can be illustrated for discrete variables by considering the experiment of tossing a green die and red die. Let the random variable x represents the outcome on the green die and the random variable y represents the outcome of the red die. Then x and y represents the product of the numbers that occurs on the pair of dice. In the long run, the average of the products of the numbers is equal to the product of the average number that occurs on the green die and the average number that occurs on the red die. Corollary 4.5, let x and y be two independent random variables, then sigma x and y will be equal to 0. And thank you.